Hello everyone, I'm John Everest and I would like to share with you some information on high dynamic range images for lighting analysis. It's going to be sort of a series of, I would imagine, just four very short presentations. It's basically just an extended version of a presentation I sort of gave a few months ago, but I didn't want to waste the knowledge and the methods, so I just thought I'd put it on here for anyone else who wants it. What I'm going to cover is what is a high dynamic range image, why is it useful, and how can we use this in lighting analysis workflows. Let me give you some context. A JPEG image is what's called a low dynamic range image. And what that means is it has a luminous range of 256 steps between the brightest and the darkest point. We call it low dynamic range because by comparison a high dynamic range image, or the format of high dynamic range I'm going to talk about is the Radiance RGBE format. That can make a transition if it needs to in 77 million steps. So you can see why one is high and one is low. Now, here's a simple classroom that I've just made. It's physically accurate and it's just generic in that it's got some lights in it. It's got some daylight, and we look at the board at the front of the classroom. There's some perimeter lights at the side. Excuse the formatting. There's a few bad ones. I changed the template last minute. And straight away I can go into that image and I can sort of say a high dynamic range image has the physically accurate luminous data in the pixels. So I can straight away ask and just say, show me the extremer points, show me the very brightest and the very darkest. If anyone's wondering why I've got such a bizarre low level there, 0.001, which is basically as good as pitch black to our eyes, that was a modeling error, and I sort of left a gap between the duct and the bulkhead, and the computer was actually seeing inside there. So if we were just staying with a JPEG image and I said, well, I need to see some more detail in the shadows, well, I would have to forfeit all the luminous data for anything that wasn't a shadow. So if you look now, like under the chairs and the desks, yeah, we can pretty much see what's going on there. But the penalty is we have burnt out virtually absolutely everything else in the image. I can step it back and say, well, so maybe just show me the mid and low tones, and it's a little bit better, but we lose some of the data in the very darkest bits under the chairs, for example, but we see more of the rest of the image. We start to move in the other direction and say, well, actually, I'm interested in the mid to high tones, and we've totally lost everything on the floor, really, haven't we? And we can say, well, actually, I'm interested in the very brightest, the detail of the very brightest points of the image, and yeah, we lose everything else. So what I'm showing you here is it is impossible to squash with any meaningful accuracy all the luminous data of an image into 356 steps or a low dynamic range image. And even when you have a high dynamic range image with that 77 million steps, a monitor can't show that to you. So what it has to do is something called tone mapping. And tone mapping is just sort of is squashing that high dynamic range image into a meaningful representation to the limitations of a conventional monitor. And this is how, when you go into HDR mode on your iPhone or your Android phone, this is what it's doing. Is it's taking the image at multiple exposures and it's taking the detailed areas from each bit and displaying it to you like that. So with an RGB image, like I say, because we're capturing the physically accurate data in every single pixel, we can actually start to think of the pixels as a calculation point. So if we have enough pixels, we can actually start to build up a very, very, very dense calculation grid. There's a few caveats to that. There's it's beyond the scope of this presentation, but there's a little bit of interpolation and extrapolation going on there, but that is accurate enough. There are many tolerances in a lighting calc, and that is a physically accurate calculation, physically accurate sort of calculation grid for our purposes. Right, I'm going to cut the presentation here, and on the next one I'm going to show you some of the useful things we can do with a high dynamic range image now that we know we have that useful information buried in each pixel. So I'll see you on the next video.